Just not to forget, start the recording.
I can always cut off the stuff.
Yeah. That's a sort of trivial issue. Beginning and the end is easy to cut off. For the cutting off something in between, you need some specific knowledge. Ja, computer moet daar blijven. Dat, anders kan ik niet alles opnemen.
Ik hoorde van Oscar dat er een seminar was gisteren.
Ja,
Over zo logische vergelijkingen.
Ja.
Is dat opgenomen? Of niet?
ja,
Want ik wou, ik kon niet te veel afkomen, maar een beetje ziek geweest.
is opgenomen. Vraag het maar aan Giovanni. Giovanni maakt de opnames. Maar we zijn nu begonnen. So we started in making a website for our seminar. And the plan is to put all the material on the website. Of course, if the speaker refuses to be recorded, there will be just the abstract, maybe the slides. Well, problem with recordings is you're doing a nice presentation. Okay. For some reason it doesn't work so well. As long as you don't have a permanent position, you don't want to show it to the rest of the world.
Oké. Zo, een beetje opletten van te veel. Ik hoef het niet zoveel, maar het zal het wel. Gisteren ook moesten campus vluchten, dat zo, weet je wat zijn wat? Campus vluchten. Nee. Zo, ik ben echt wel oude bakbeurt, zo de tegels, de klauwen. En ook als ik de ramen open, dus ik wil ja, zijn zoveel mensen. Ja, maar dat kan wel nodig, het duurt toch maar gewoon.
Vorige week stond de verwarming gegaan en de ramen open.
Ja, dat is een moderne manier van energie Hey.
Nee.
Ja.
Zo, bij zo Ramsey-functies en zo, daar gaat het erom van dat in sommige gevallen bewijsbaar is in, bij de jaarwachtschema's en in sommige gevallen niet. Maar wat is er als een functie bewijsbaar is of berekenbaar?
Ja, kan ik niet zo zeggen. Maybe we wait until we are more or less complete. I think we still wait for some participants. So I will start in 1 minute. Yeah, maybe I start. So before we continue, let me just explain this big picture. The questions for application. And we have seen 2 examples in the ferrocerican of dimension 2, Cannonball-McLuhan for dimension 2. And these theorems are linked to the Ackermann function. In the sense that in the normal formulation, the Ramsey functions are bounded from below by the Ackermann function. Now, what is the relation to arithmetics? Well, we have arithmetic. What is this? Usual axioms for usual successor plus times and induction for formulas. And there's a subsystem which is called I sigma 1. Different versions of it. But this is a subsystem EA where induction is allowed for formulas containing at most 1 quantifier. Especially, this induction is allowed for formulas which are called sigma 1. Sigma 1 is the closure of, let's say, prime formulas, closure under propositional connectives, bounded quantification, and 1 unbounded existential quantification. And this is all more or less equivalent. And the basic result in group theory, which we will not cover, is if I sigma 1 does not prove every m exists n such as the Ackermann function of m to n. So the totality of the Ackermann function is unproven in I sigma 1. Now one has to formalize what does this mean, right? You have to write down the defining equations for the Ackermann function. Formula of arithmetic, a sort of routine procedure for this. And then you can basically say, what does it mean that the Ackermann function for value m produces an output n? So if m and n are given, you can write down the graph. And it's one of the famous results in proof theory that I sigma 1 proves the totality of all primitive recursive functions, but not of the Ackermann function. Now, since I sigma 1 is not able to prove the totality of the Ackermann function, I sigma 1 does not prove this one and this one. Now, this lecture is about these phase transitions. So we don't do the proof theoretic part in this lecture. So we don't prove this type of results. What we will do is we prove lower bounds for these principles in terms of the Ackermann function. And since they are growing quicker than the Ackermann function, these principles, they're all for all exist statements. These principles are also not provable. And so we get some famous results on that these principles are not provable in one quantified induction. Anyway, this is a big picture. Is this answering your question?
Very first, are you recording?
Yes, I'm recording.
So if you cannot prove this,
Yes.
So can you then like assume the opposite, and then you will not have a contradiction if you assume the opposite, because otherwise you would be able to prove this. And so when we say like it's true but we cannot prove it, that it's can we not only can we also not assume that it's not true because it's not provable?
Yes, we can assume that there are models of this theory in which the Ackermann function is only a partial function. Yes. So there will be function values which are so big that you cannot reach them from below, say. And these will be these non-standard models where you plug in a non-standard value for m, and you would need a non-standard value that's so big that it's beyond your model. But that's just sort of underlying explanation. But for this lecture, don't worry, no proof theory is needed. No referring to formal systems. We just do finite combinatorics. But the motivation for the combinatorics comes from arithmetic. Now, what did we do last time? Last time we studied the Kanner-Moe-Maclaurin function for F regressive partitions. So for input M, there's at least R such that all partitions P. If P is F regressive, then there exists an H, which is minimum homogeneous, and I forgot here to mention what is the value M. The homogeneous set has, of course, at least as many elements as M. Now you can ask, given M, how big is this R? And this R is surprisingly big. So if F is identity function, then it will be the Ackermann function. Now what did we do last time? We studied the modified Ackermann function. Ackermann function with respect to some epsilon. Epsilon is a number, as usual, strictly positive. When we assume it's bounded by 1. It's not so strict, not so it's important that it's strictly positive. And then we start with the successor function. That's the starting function. And then if we start looking at the function with index k plus 1, we iterate the previous function, but not n many times, but n to the epsilon many times. So this is a bit slower than the usual Ackermann function. And we will see in a minute that this is still Ackermannian growth. And last time what we saw is if you have this function, or here G epsilon, and if you study Cannon-Maclaurin with respect to G epsilon, this grows like an Ackermann function, namely if you combine it with the standard Ramsey function for PS, so basically an exponential function in N and C, then we get an approximation, a function value which is bigger than the C plus 1 branch of the Ackermann function with index epsilon. Now what we do today is we make this result sharper. And for the next result is so let F be a function. Increasing. And assume f of I is bounded by the normal Ackermann function. So now write this. And assume. Now this is a side assumption, which I will fill in the next chapter. Namely, if I take the Ackermann function, this one, or index 1 divided by I plus 1. And now the index is what? F plus E square plus 5. Bigger than
does the arrow mean that the function f is increasing?
Yes.
Or maybe. Oh, it's
it is increasing, strictly increasing.
and the assumption is for all
This one?
I? No, in the first line. So
Yeah.
fi is
You're right. So for all
it's strictly increasing.
yeah, the article is weakly increasing, but then you have to figure out what's going on with F inverse. And when it's strictly increasing, there's not a slight problem. The F inverse applied to F of I is I. Otherwise, it's sometimes to modify it slightly, but this is not essential. To assume this one for all e bigger than 0 and n bigger than, and then comes your sum. Numbers maximum 4, 3 plus 1, 3 plus 1, 2 plus 1. Assume now f of I is I to the 1 divided by f inverse of I. Then knowing the u with respect to function g combined with Ramsey function R2 I plus square plus I plus 5 4 plus 5 plus n plus 5 plus 1 plus 1 plus 3 is bigger than. Now there's a bit of noise in the formulation. Oh, these terms here, they look a bit ugly. They are ugly, but they come from some technical verification. What is the upshot? The upshot is the following. Assume simply that f is here the Ackermann function itself. Now we study this function g of I is I to the 1 divided by the functional inverse of the Ackermann function. So what is this function compared to this function? Well, here's fixed epsilon. Here's somehow an epsilon which converges to 0. So this function is in the limit below this function. And then what we show is it's kind of a Green function for this function g, and some input which is basically exponential in I is bigger than the Ackermann function. And not only this works for the Ackermann function itself, but it also works for primitive recursive functions. And of course, you get here primitive recursive upper bounds. But we are mainly interested in the version where we get Ackermannian lower bounds. So f of I equal to the Ackermann function of I, that's the most important. Now, how to prove this? The proof is basically a one-liner coming from this one. This one proves this parallel. Now, we don't see this, right? So therefore, I give the proof. But don't worry, the proof is rather short. So just putting 1 plus 1 together. The proof. Oh, this Aggie notation is somewhat put into functions. Now, no. Now the magic starts. We say we assume that this is wrong, and then we derive contradiction. Assume what AMG of R2. Then we have here what and PIE. This one is listening. You want to derive contradiction. Now, from this N of I,
Does it need to be Fi plus 1?
yes. Yes, and let's be careful. In Webber theory, plus 1 matters. If you count one in the wrong way, you are lost. So, but anyway, these results are stable under small modifications, so it's not so dangerous. So, what does this mean? Well, for L less than equal to Ni, we study F inverse. So L is less than equal to this number, L is less than equal to this number, then L is less than equal to this number. So this one is bounded by F inverse of F of I plus 1, so this is I plus 1. Hence, for this L, we have what? L to the 1 divided by I plus 1 is bounded by L to the 1 divided by F inverse of A. So that's sort of easy estimate. That's the usual trick. So as I said, this function finally below this function, but in the beginning, this function grows quicker than this function. This is what we use when we have what? AMD of R plus. Okay, so now we consider G regressive functions on this domain. Looking for the pi plus 3. So, yeah, plus 3. Let's take here also plus 3. Yeah.
And like statement of the corollary, we also define function G, but then in the proof, G is defined differently. So
I think that's the Q.
Yeah, let's see.
just another level.
This is function G, right? Okay, so we take this function G.
But now we have double defined, no?
Yeah.
So that
Oh, this one Q.
okay.
Yeah, so there was a bit of this. So this Q is this Q. Initially should somehow be okay. What is the important message? The important message is we assume that in the beginning the function G is dominating this function. And if you have a function which is regressive for a small function, and of course it's also regressive for bigger function. So it means if you have Kanamori-Maclaurin for a large function, it dominates the lower function. We have one function here was G index epsilon. So we now replace something G by G index 1 divided by 1 plus 1 RQI plus Q. If we use the theorem which you proved last time, then we use this type of estimate. Is bigger than, but this function is bigger than I plus 1. And we get continuity. So that's a sort of magic. So if you have proved the result for fixed epsilon, you can move this epsilon into the dynamic function, namely an epsilon converging to 0. Now what is left is basically to explain why this function here measurizes standard Ackermann function. And this will be part of the next chapter. We study this in more generality. This first chapter was about Ramsey functions, and now we study phase transitions for the classical Ackermann function. And we study right from the beginning infinite collection of different Ackermann functions. Yeah. Phase transition related to the Ackermann function. Now, for this purpose, consider two functions. G from n to n. And now assume for simplicity G is strictly increasing. G of x is x and equals x plus 1. G is a function which we are going to iterate. And then G would be the identity function, and to iterate, it would nothing, never produce. So therefore, we assume that G grows a bit quicker than n. H is considered to be weakly increasing. Because you want, this is really important, not really important. Morally, it will be weakly increasing, but every now and then it's not fully weakly increasing. So just H is some function. H is just some function. Think about H like a log function, for example, or a square root function rounded to natural numbers. Then we find EH x. X is a natural number argument. So G is our start function. And in some sense, we are setting up sort of dynamic system, then we iterate G. And iterate and iterate. And we want to know what's coming on it. So we define BGH, branch A plus 1 by x, takes the previous branch, iterated h of x many times, by x. And the limiting function is just x dim. Okay, and now the question is, given G, for which function H, the resulting function primitive recursive or non-primitive recursive? So it's either going to have growth exceeding all primitive recursive functions or bounded by primitive recursive functions. Now, what we need already that for h of x being x and epsilon, and g of x being successor function, that VGH is Ackermann. Now, what we do is the next step is the obvious thing, namely, you put makes this epsilon dynamic, like we did it here. We replace epsilon by 1 divided by the function inverse of the Ackermann function, and then we will show that the resulting function is still Ackermann. This also holds for h of x is x to the 1 divided by Ackermann inverse. Okay, that's the goal. And if we replace here the Ackermann function by a fixed branch of the Ackermann function, then the resulting limited function will become primitive itself. For h of x and e of x being x to the 1 divided by e branch of the Ackermann function, we obtain that b between this function p and t is primitive inverse. So that's already difficult to prove. And now let's see. Yeah. So what are we going to do? We fix functions g. So let the binary length of x be given as takes the binary log of x plus 1, and then we round up to the next integer number. That's the standard binary length function. And now we can iterate the binary length function. Index L plus 1 is we take the L times logarithm and apply another logarithm. With understanding the zeroth iteration of the log function is x. So these are slower and slower functions. G0 of x will become our function x plus 1. And gk plus 1 it will be 2 to the dk of logarithm. So what is going to happen here? Basically, the idea is as follows. So V0 corresponds to x plus n. V1 corresponds to 2 times x. V2 is essentially x squared. V3 is essentially the log of x squared. V4 essentially 2 to the 2 of log of x squared, etc. So what turns out, all these functions gk is strictly bound eventually by the exponential function, so they're all sub-exponential functions. But jumping from gk to gk, from gk to gk plus 1, you get speed. And this is our scale we want to consider. So we want to figure out, given the function gk, what is the phase transition with respect to the function h? And it turns out the phase transition will differ. For every k, we get a different description of the h. It makes these functions interesting. Okay. Now, first let us consider this type of result. So there will be some sort of brute force construction now. Well, now you just look at this definition. It is given by recursive equations, recursive functions. So when you want to prove something about these things, you cannot just do a trick. You have to go into the equations and verify what's going on. And so I use a new version, the Ackermann function f of x. The Ackermann function, where I start with g. G will be the exponential function. Okay, you written. I mean, I write this way. And the iteration function will be the identity function. Okay. So the next theorem is as follows. Assume you have function h, d, and l. It's written down. Take x and takes the l and iterate binary length, so the log of log. Then we take this one to the 1 divided by
Excuse me, what is the first argument in the B function?
an exponential function
Okay.
where x of x will take x. Yeah. And here I have this one. And it's right v k of x is v. We take our function gl from there, and this function h BL. And applied this. We write down number C. E will be a big number. The maximum you could play. What? But it's not the maximum, it's just. Two L. Ah, yeah. So I have here this iteration of the log function, but I have also an iteration of the exponential function. 0 of x is x, and 2 L plus 1 of x is 2 to the next n of x. So we take 2 index L of fg of 2 to the k plus 3. Then we have all x, and this is the case C, and I is equal to it's L 1 divided by fg inverse of L times iterated by length. That what? E D L a branch L times iterated is bounded by 2L of viral length of x L times iterated plus x L to the k plus 1 divided by fg inverse of xl times I. Oh, what does this mean? It means finally function BL is primitive recursive. We have this bound for if you have this bound for this number for x and it's as big as c, then
the estimate below index D, you
yeah.
don't mean the same as
Yeah, so fd is the x function dx minus deep branch in the functional description of this one.
And is there an argument for the 2L on the end? Is there an I or I can't read that?
Yeah.
Yeah.
It's 2L of we have this function 2L of x is
Yeah.
term of 2's. And this is the argument. So we have 2, and this is on top exponent. And times number I.
Ah, times I, okay.
It is this number I or E.
Does I above the BL, is that exponent or?
This is a number of iterations. So it takes this function, the case branch, and the ith iterator for this. One by this one. Now, what we can do is we can finally plug in the number c. And then we get here a term. We can plug in the number c over here. And then we see, so this number c, if d is fixed, is a primitive recursive function. And then this bound will be primitive recursive in this number. Then we are basically done. Now we have to prove this one. So that's a sort of specialized. So well, when I did this, well, I just somehow started. I did some calculation, and then some terms showed up, and then I had to refine the calculation. You calculate until you hit the final result, or if you don't find something, then there's no result. So finally we have what? L K of K bounded by B L K of F D K plus 2. This is bounded by times F D let's see.
Is this a proof we're doing? Or?
Well, just well done. So I want to say that this function is primitive recursive. Why does it follow from this one? And for this, we plug in basically a number k. So the Ackermann function. Then we make this internal argument bigger. We plug in number c. Then we use the estimate. And when you see that there's a function of k, this is bounded by a fixed branch of the Ackermann function. So this is bounded by primitive recursive function. And therefore, we should be fine. At least, I hope so. Let's look at to improve this one by induction on K. So to prove this one, induction K is K equal to 0. And now, if you have PD 0, now what? PDL 0 is GL, right? We have L0 is G of X. G of X. We direct this finally time. Okay. K is equal to 0. Now we prove this one by next induction on I. And there's another induction on L. This one. So we have induction on K. I, L. So let's see. B 0. 0. So let's say I is equal to 1. L is equal to 0. And I have this number. This is 0 of X plus 1. This is bounded by 2 index 0 of annual length 0 times integrate. This is X plus something. And now I assume that this term here is as big as 1. That is fine. Okay, now bigger than 0. Then VPN 0, 1 X is what? It is yellow X. It's 2 to the L minus 1 of binary length. Now here we can apply induction hypothesis for L. And this is bounded by 2 to the 2 index L minus 1 of the L minus 1's iterate binary lengths. Like let's see. There's this one, right? And here we take, so the argument X, then the L minus 1's iterate of the binary length function coming from the induction hypothesis plus X, the binary length of X. And for this, we take the L minus 1's iterate binary length, the FD inverse of X L minus 1. And now, if you take the binary length function of X and iterate the binary length function L minus 1 times, we get the L iterate binary length, also here the same. This is bounded by L XL plus XL 1 divided by FD inverse L times iterate binary length. That's good. So that was the case where we have I equal to 1. And in the case I equal to 1, and this is induction L. Now I do the induction state for I. And obtain what? dEL 0 I plus 1 of this is what? dEL 0 applied to L I times iterated applied to this. So I plus 1's iteration is 1 iteration plus I's iteration. Here I apply induction hypothesis. So it's VL 0, which is nothing else than GL. You can write GL. Here I get the term coming from the induction hypothesis. It's 2L XL plus XL to the FD inverse of XL. Yeah. Now what is GL? Yeah.
Yeah, just one line, but I see one.
Yeah. So let us consider what is GL. L of X is basically 2L of XL. Correct. We had GK plus 1. This was 2 index GK, 1 index. So we get more and more 2's, more and more iterations of blocks, and it's the moment G0 we have success. So we get this by induction on X. Right? So should I write this out? It's this one as this description, or is this here? So this is a definition. And this implies the GL as this explicit form. If you don't believe me, so induction in L equal to 0. So G0 of X L is 0 and this L is 0, then we have here G0 of X 0 X 0. Now, induction step GL plus 1 of X 2 of GL of final length of X. So it's what? It's 2, and then here's L of XL L times iterated binary lengths. Now we have to apply it to binary lengths. plus 1. So by induction hypothesis, GL of binary length of X is 2L. L times iterated binary length applied to the binary length of X plus 1. And this is 2L plus 1 of L plus 1 times iterated binary length applied to X plus 1. So we get this formula by induction. Well, why I need this? I need this right now. So I have this messy term here. Now I have to look what is function GL. GL is producing 2 in index L. Now we apply L times log function to this term here. So we kill this tower here. You get this inner argument. Plus 1. Yeah, and now this plus 1 can be moved into this factor. So since X is big enough, can replace the plus 1 by times the plus 1.
Why should the inner factor be like put between implied the function binary log and well it's one function.
What? So
So
what I do here is basically I kill. So I take this description 2L of binary length. So the binary length kills this 2L. So I take this term, and then I have this term, and I have plus 1. So this term is the same as this term. And this 2L goes away with L times log iteration. But there comes this plus 1. And the plus 1 is just this one. Now, it's not so dangerous because X is assumed to be big enough. So I can assume that this term here is bigger than the 1. Then I can make this upper bound. And this is the bound, which is this times I over here. So I plus 1 iteration gives a factor plus 1. So what does this mean? This means we have proved the result in case that k is equal to 0. And now we introduce the k is equal to k bigger than 0. And now assume k is bigger than 0. Now what are we claiming? We're claiming this inequality. So we do next induction on I. Okay. So what? B D L of A to I, in this case I have to have this expression. Now we can use our induction hypothesis for k minus 1. So we write the k branch of the Ackermann function in terms of the previous branches. We have k minus 1. And I have to plug in the function h applied to x. Function h applied to x is L iterated binary length to the 1 divided by FD inverse of L. Get here a rounding of x. And what is here the trick? The trick is, of course, now this index I here goes as a factor of E. This explains somehow what's going to happen. So this is now going as a factor downstairs. And then it fits nicely together. So this is bounded by induction hypothesis K 1 by 2L XL plus XL to the K divided by F the inverse of XL times. Now this factor comes into play. And now he makes this one bigger. So the applied induction hypothesis k minus 1, we got 2 to the k, and for k, we're allowed to make 2 to the k bigger than. So this is bounded by 2L. And stuff. Here I replace 2 to the k by 2 to the k plus 1. That's it. So here by this product, you get this term, and the exponent you get the plus 1. So it's 2 to the k plus 1 divided by this one, but 2 to the k plus 1 by the k plus 1. So you get this way. And this was the case I equal to 1. How comes the induction step? And but what you learn by this construction is a bit how I obtain these terms. These terms here are coming from, well, I have this bounding function HDL comes from over here. So I have to organize it somehow in the term in the institute. Well, now what? L K I plus 1 X is L K of E L I. Okay, we apply induction hypothesis to this term. And then we look at the definition of this term and go down to the iteration of the previous branch. So that's bounded by the K. It comes in that one, this L plus XL, okay, plus 1 divided by inverse of XL by. Okay, now this number, it's y. And continue somewhere here. So, dus die afshot. Die. It's what? This inner term is y. And now I apply the definition of this function. So I go to the branches. B, E, L. Okay, minus 1. Then I have here y. L times the great binary length 2, 1 divided by 15 y. So many iterations. Right. And this looks ugly, right? But the point is, this situation, we have here the possibility to apply the main induction hypothesis on K with respect to this number I. What do we obtain? We obtain L of YL plus YL the K is inverse of YL times what comes the I is this one. So L inverse of L. Now what? Now what? We look at what this one. Y is this complex term, but it starts with a 2 next L. So we just zoom in the first one. So this is bounded by L of XL plus X plus 1 F E inverse of XL. Fine. That's this one. And this one is this term of the 2 K plus 1. So that's YL K plus 1 divided by N inverse of Y. Aha. Now, what do we have to show? You have to look at this expression. And the first terms look good. In the meantime, we have I plus 1, here's I. So we have here an additional space of 1 plus 1. So if you can show that this term here is bounded by this term, then I'm done. So to show only by L K plus 1 divided by FT inverse of 1 one length bounded by now the term in X. Yeah.
I was looking at the set from at the bottom of the most left blackboard, so we use the definition of the K minus 1 to write this out, and then we apply the induction hypothesis with respect to K.
But here we do what? So the induction hypothesis is slightly where we move this term into the one. And that's the induction hypothesis for I plus 1. Then we go into the definition of the first iteration. This one here. We spell out what this is, and then we apply induction hypothesis for K minus 1. So we move the first iteration into this term here. Apply to this Y. And then we apply induction hypothesis for this K minus 1. And we get an expression in Y. Now we have to relate the Y's to the X. And what we did here is we zoomed into the first Y. Y is a 2L tower of something. We kill the exponentials. And we obtain this term from this term. Now this term here is giving 2 to the K plus 1. And then you get so this product is just same as this.
And where do the Y's find?
What?
Where do the Y's
The Y is just application to this.
okay, that's okay.
That's the one definition. It's not. It's just otherwise. So the situation would be even more ugly.
Also a question, because when you apply the induction hypothesis for Y, this only holds if B is weakly increasing, right? How do we know this?
What is weakly increasing?
Well, you fill in B, D, L, I, K with the Y term, right?
Yes.
And that's the induction hypothesis, but it's still a function argument of B, K.
Yes.
So this only will hold if B is weakly increasing.
Yes.
And how do you know this?
Well, that is an implicit assumption. I didn't show it. So well, one has to do an extra verification that the BD functions are weakly increasing. But you are right. Formally, one has to show this.
But it's the case that it's
Yeah.
weakly increasing. And you don't have to assume it, it's always the case. Or?
Well, normally the point is the definition of the B hierarchy is based on increasing functions.
Mm.
And therefore it should be okay. Well, I will check, but this I didn't prove yet. Anyway, we are here. This remains to be shown. So, white or whites. I contains an I. And we have some exponent. But this y I is estimate. So this I can be measurized by adding here plus one. Now for the exponent, I have here 2k plus 1 ft inverse of yn. And now the point is I want to replace this YL by X. Now FD inverse of 1 at least as big as FD inverse of X. The inverse of the why is this the case? Because FD inverse is weakly monotone. And consider the else logarithm applied to y, and you get this term. So this term is L equal of x, L logarithm applied to x plus something. And the inner term is bigger than this term. Therefore, I can make this term bigger by replacing It's by x. So, on the other hand, I have this term. So, if I can show this one, this term is bigger than this term, then I'm done. So I have to only to show this one. Now, why is this the case? Good question. So here I kill this one with this one. And I move what? This one over here. So what is left to be shown? So, is that L plus L K plus 1. By F inverse of L is bounded by L K plus 1 divided by K plus 1. Now, why is this the case? It's a tricky business. This exponent here is strictly bigger than 1. So this term here kills clearly this term. Now, what's going to happen here? And this term becomes rather big. And this somehow goes to infinity. So therefore, the whole term goes to 0. And then XL to something is dominated by this one. So now we have just to figure out when is this term becoming much smaller than this term. And for this, it's good to have that x is at least as big as this term. So this follows from x L FD okay, so that is the proof. And now, what are the comments on this? The whole proof is ad hoc. You see, there's a brute force calculation. It is not suitable for generalizations. So when, let's say, consider hierarchies, transfinite indices. So what I will offer as a project is an alternative proof of this one, which is much cleaner. So now you see, this is an example for an ugly proof where you do all sorts of brute force calculations. You go, so to say, into the definition, but you have not really a good feeling of what you are doing. And anyway, that's the case that the limiting function is primitive recursive. And now we do the opposite, namely we show when we replace this function by the inverse Ackermann function, then we get Ackermannian lower bounds. And that proof is much easier for some reason. But I will do this after the break, because now it's already long. So, and of course, in the exam, you're not supposed to do such calculations. It's just, I hope this is a nice calculation somehow. And so you go into the meta. What is the Ackermann function? The Ackermann function is defined first by recursion on the branches. That's the main induction. Then you have induction on the iterations. It's a substitute induction. And this, what makes it here complicated is we have also the functions GL, which also define by recursion. So there are 3 recursions involved. And when you want to simplify the argument, the easiest way is to do the whole proof just with L equals to 0. And it's the most easy. Okay, so now 15 minutes break. And after the break, it will be more easy going. Okay. Now you ask, how did I come to these calculations? Well, the point is you have to make a guess what the phase transition is, and then you have to verify it. So this is a brute force verification.
There was no reverse engineering involved in finding the upper bounds.
Well, there was reverse engineering involved in the sense that I had the result which I used to Kahneman McLuhan is only and others. And we knew that this function was producing Ackermannian lower bounds. Then I had my general strategy to replace epsilon by something like this. And then the only problem was the hope was that this was sharp, and this reverse engineering in the sense that gave me the conjecture this should be primitively recursive. But the problem is then you have to verify it, and you have to take whatever you have to fit it. And unfortunately, I just started somewhere and did a long calculation, somehow it came out. But yeah, so every now and then you do this by brute force. But there will be a much more elegant proof. But it has to do with ordinals, but you will learn ordinals in the next steps. So at the moment, we cannot do the proof because we have not the theory of ordinals available. And ordinals are structured in the universe for whatever reason. You look long enough into the ordinals, some nice stuff comes out. And it comes with a nice clean proof of this. But anyway, it's will be the project for this course. So don't worry, it's not calculated like this.
Are the projects solo or are they in group?
Good question. I haven't decided yet. So, maybe it's in groups, but then a little bit more. But it depends on. So I can do it either way. Whatever you prefer. I have not written up the project yet. So Philip did not make it to the lecture. Too early for him. Yeah. Yesterday he claimed he wants to make.
Well, if he wants to, but don't think,
Physical obstructions.
don't think he has enough willpower to make it.
Yeah.
You mentioned at the start that I sigma one doesn't prove.
Yeah.
How are you going to cover that?
Maybe I cover it in the next course. So say this course is basically about the famous independent result, how they are connected to functions like the Ackermann function. And so this course is the course on elected topics, but there will also be a course on proof theory. And the course on proof theory, I will cover the classical results on the arithmetic and also sigma 1. So, have you ever seen it? Have you seen the result on sigma 1?
No.
Oh, I see. Well, this is sort of one of the highlights of proof theory. Also not easy to prove. So, but so this well, there are different methods to prove it. One is by what is called partial cut elimination. Have you seen the classification of the provably total functions of PA? The classification of the provably total functions of PA. Have you ever seen this before? Not doesn't matter. Well, this is requiring full cut elimination. But for the fragments of PA, you have to mix cut elimination with cut elimination for predicate logic. Say twofold cut elimination, something called partial cut elimination. So the point is, in general, you can consider all fragments of a PA, which are called I sigma n. And for all these fragments, we have a nice representation of the provably total functions. This is all covered in the lecture. Coming next time.
Algebraïsche en zo bent met de topologische exponentiële graaf.
Maar net in pas in je plek aan bent. Nou, dat wil ik niet op. Je hele betrokken kijken ook aan het. Toch, daar is natuurlijk lang aan een bakvlog. Maar kan dan nog gewonnen. Alles. We zijn nog niet bezig met misschien gaan we wel doen, maar niet zijn al dit wat kunnen theorische tool. Okay, we are back. So now we have covered let's say the case where the limiting hierarchy was weak. Now we want to consider the case when the limiting hierarchy becomes strictly flowing. For this, I recall the definition. So GL, basically parameterization of our starting functions. We start with the successor function, then we have 2 times x, x squared, and these are all sub-exponential functions. And the function GL is put at its base. Then we iterate this function, iterate and iterate and iterate. And so we get a sort of Riemannian diagonal function. So B L of x is the diagonal function. And now we control the number of iterations by a function h dl of x. Where h dl of x is the following. Take first L many iterations of the log function, apply to x, and then we take the root. And then we round to the natural number. And that's it. And our claim is in all these situations, this function is like a Riemannian function. So it's a rather interesting result. And you see, when you vary the L, the function HDL ordinarize. So the higher the L becomes here, the more iterations of log are you getting here. And all these functions are different. So you get an infinite scale of Ackermann functions with different phase functions. And finally, we make the D into the inverse Ackermann function depending on x. Okay, that's the plan. And yeah, for some technical reason. So as I said, we are dealing with the binary length function, log function whatsoever. So there are technical rounding problems, which are sort of annoyances. Assume basically, and this is really not interesting. We give the L iterate of a binary length function 1 over D. We round and take it with k minus n divided by D. And basically, we want to have the L times iterated binary length function applied to L, but here's the small stuff taken off. So this 1 over D, I want to put it over here. I want to get k over D, but this is usually a bit smaller than this one. But if I take a factor smaller than 1, then for large enough x, this is always true. And this holds for some numbers x and some constants KL. Okay, and so there will be for given k and L constants, this is always holds for all D. Anyway, these constants are not big, so it's primitive recursive. Okay. On the plane theorem, we have what? B, L, 3 times E plus I plus 1, L x over D. This has been present. L of standard Ackermann function AI x. What does this say? So you have to look over here. So here's the normal Ackermann function in I. Here is our modified Ackermann function also in I. But we need some starting points. So we have to make the index big enough so that the majorization behaves as expected. And this holds for all x that is as big as the maximum taken to whatever we have here. This constant here, which are small, and here we have a lot. This some iterative exponential stuff is not so important. But basically, this shows that the Ackermann function will be lower bound for this hierarchy. Okay. So we have here this GL of x. Now GL of x has a nice behavior. What is GL of X I times of iterated. This will be L XL plus L. Why is this the case? Well, it follows by induction on I. If I is 1, then we use the property over here. It's fine. Induction step. What is GL of GL of Fx? It is what? It is GL. And let's now for this. We have here 2L of XL plus I. Almost. This is correct, right? Okay. Now what we do is we take the outermost 2L, then we take the L times iterated binary length. We have 2L. Then we take this 2L power and take the L times iterated binary length function, so we kill this off. And finally comes plus 1. And here we are. So you see, one can easily write down what are the iterations of the GL. And then you see also basically what the nature of the GLs is. They form a natural hierarchy which are somehow stable under some sort of iteration. And the higher the L becomes, the higher the tower becomes. And yeah. Okay. So what does this mean? Yeah, so that's and we will have X, and therefore the same. Now these functions are still not spectacularly quickly growing. So this is still, you have to be careful. This is still not an exponentially, so I is fixed. It's not an exponential function. It's a sub-exponential function. Now to make this hierarchy growing, if you ever want to do this result, you have to show that after some bootstrapping, and often enough, you leave the world of sub-exponentials. You have to generate an exponential function. This function is not an exponential function. Anyway, now comes the next trick. We show what? Well, I have here this bit of an ugly estimate as 1/2. And if I iterate this, I get a bit more ugly terms. Anyway, the claim is I take BDL. at least as big as L. Here I have some 1 divided by k. Okay. Times I times x over d plus what does this mean? You see here, in the beginning, I cannot build up speeds. Now, if I go higher with my indices, I get here XL K divided by D. What does this mean? When K becomes at least as big as D, I get here more copies of XL. Slowly, we can imagine that the process starts growing. So we are still in the bootstrapping procedure, so let us first pause. And this holds for X big enough. Let's see. Okay. So, induction on K. And another player, there is a subsidiary induction. Okay, now we do this. And induction plan is 1. And I is 1. In the L 1 is what? It's 3 in the L is 0, and here comes this function applied to x. Now we use this property here. It's at least as big as yeah, we have to plug in for I this number. This is ugly rounding. And this is at least as big as this term coming over here. Another 2. It's L1 over here. So you see these numbers here playing a big role. It's just because there's some nonsense going on the surrounding, and for the rest doesn't play any role. Now comes the next one. BL. Here is 1, but now we do subsidiary induction on this I plus 1. So what's going to happen here is here BL and 1 of BL. Okay. Now we apply induction hypothesis for I, this term. Getting what? EBPL. One. Of. L. Oh, yeah, right over what is written here. Divided by times I times X. Plus. And now we use this estimate here. And oh, I don't know. Others. Now we have to take the whole argument. Takes the L iterate binary length is 1 over D. So take this one here. Then the L times iterate binary length to the 1 over D. Is this term here? Plus the L times iterate binary length. Same term. Okay, now what we do here is this L times iterate binary length goes away with this one. Let's see what's going to happen. So this one here goes away with this one. Now, make it to L. 1 over 2. Forget about this term, we only take this term. Plus, we look into this term. Log was raised to 12, we get this flat term. And what we see is here times I, this next one. So this is as good as L 2 is 1 over D times I plus 1. So every now and then we throw away information. So we threw away information was term, just do that one.
Fine.
Wait, and how can we bypass the second to L and then skip all the other terms?
So this 2L goes away with this. This term here is just going down. Right. So this term here is this term.
Mhm.
And this term here is simplified. In the sense, the 1 over 2 is this one. 2L goes away with this root. We just look at this one. XL and this one. A bit of tricky, so just forget about this one. What remains is XL to the 1 over D. So one trick in all this estimate is you have to decide what to throw away. And when you throw away too much, you're lost. But anyway, fine. Okay, it was the case for k equals to 1. Now induction step. Take those 2, take those 1. Again, we do subsidiary induction. So what? We have E, D, A, E plus 1. It is E, E, N, A, here we have L, 1 over D. Like this. Now we apply our induction hypothesis for K. The upper index I goes into a factor. And that is the important point. These factors here, they produce larger and larger terms over here. So this term comes down here, so you apply induction hypothesis. L here. You have the the I comes down, which is L to the 1 over D times given from the induction hypothesis K divided by D. That's it. But here you see how the game is played. At every step, if every iteration, this I comes down as a factor. Now I do this basically K many times, and then I build up here the K divided by D. So here comes a new one, and this is the same as L. There's some innocent rounding involved. Maybe I take this 1 divided by 2 to the K here. X to the K plus 1 divided by D. That is start of the induction. Now we have to finish the induction. Continue our so we have E plus 1. It is what? It is the same as EDL. How many times iterated? This function is I plus 1. So we take one iteration outside.
get this term. Apply induction hypothesis to this other term. So you get BDF. A plus 1. And then you have L 1 plus A plus 1. Times x to the A plus 1 over E. 6L. For this term y, now we have this estimate for this function. You can already take this estimate, which comes over here. At least as big as one. If L of 1 plus 1 y 1 over d over d plus right, just copy this one and then place square one. And now what? They've here the L's rate or the way exponential. You get this term from this term. It's at least as big as what? There. K plus 1. This term here is this y. And that takes L log. This term goes away. Now forget about this one. I only take this one. So I take here x L. Take this one. Over here. Right. I replace y by x plus, and then I evaluate this term, getting now you see how nicely the word fits together. This term plus this term gives this term times I plus 1 times this term. So this is L and K plus 1. It's L K plus 1 F by D times I plus 1 plus. Okay. Now we can do something. Namely, we can make this K big enough. So when K is bigger than D, comes some equal stuff.
I still have a quite technical question with like the lower bound approximation. You're on the bottom of this board. How can you approximate? Like, how can you throw away the floor and oh wait, no, it's not there. Wait, where was it? Wait, I think it was on other boards.
Well, here I throw away the floor with the 1 over 2 points.
Yeah, no, but it's somewhere else. I think it's the other board. It's where you throw away the floor to add it like to the power of K plus 1, but I think it's like underneath that board to the left. I think it's identity. Yeah, the last step on that board, like where you the floor of the XL 1/D, and where you just throw away the like how can you throw away the floor?
I have here.
Okay. I didn't see that. Okay, sorry.
But anyway, so these estimates are a bit of. You shouldn't do so when you do analysis. Throw away lots of information. It's you should not take it too serious. Yes. Now what I'm claiming next is so morally we are basically done. So the result follows now by some estimate. So what you should learn by this is the following. You have just to read it in the right way. So what does this mean? When K becomes bigger, you produce here more and more stuff. And basically, we are starting with the function XL 1/D. Every branch of the Ackermann function gives one of these 1/D. And when you do it k times, you get basically k divided by d. Now you make k big enough. Let's say k is equal to a 3d. And you have here an exponent strictly bigger than 1. But then it's clear if you have a function like 2 will not iterate functions like those ones. They start to explode. And that is what we are using right now. So what I'm doing is first BDL of 3dx, at least as big as L of x L2 for x big enough. So, well, after k many iterations, this fixed constant, and now we make big x big enough. So we have xl 3d divided by d. So when we get here an exponent 3, when we reduce the 3 into a 2, so I is equal to 1, then we can guarantee that after some time, this function, so this is big as this function. Now, why is this important? We do, once we have reached this, as I said over here, if we iterate this function, then something is going to happen, and we do this in more general. So, claim is, take b dl, and the 3 is of course overkill, but it doesn't matter. This is at least as big as L, XL, and here we have what does this mean? And now you see you can easily generate an exponential function, because the exponent I shows up in high levels. How to prove this? Well, just by induction. Time. We have the property. So I one. It's already there. Otherwise, we have PDL dt plus 1. This is PDL of coming here. Now we plug in the estimate we have. We said there's 2L. Then we have here XL square of this term. 2L XL. Now you see this log function goes away with the 2L function. This is just 2L into the I, then square. No. It's A. I square. So this L kills this 2L, so it fixed to the I, and then a square, which is XL. But this means we get a function leaving the exponential word. And once we have reached this branch, then we can build up our exponential. So coming back to the original relation, it's already gone. Anyway,
the last step.
Yeah.
So you have in the power of 2, and it's just gone. Or
no. This L iterate of binary length goes away with the 2L. So if binary length better binary length better x, then the exponent is 2 to the I, and the outermost exponential is over here.
no,
We have this layer of this.
Usually PDI plus 1.
This plus 1 is. Indeed. Now that's what I wanted to show by that. Yes. But it's true, right? So if I have a square of this one, 2 to the I times 2 is 2 to the I plus 1. And this I said is basically this observation, which is crucial for the argument. Once you have that one, then you get that one, and when you have that one, you get everything. So what is the next plane? E L of 3 plus I plus 1 of L x to the D. At least it is 2L of AI x to the D. for x big enough. And okay, this is by induction. Now you wonder why I'm using this function, but this is the inverse function of the function I used in the iteration. So induction on I equal to 0, let's say. Then defines a bit on how we define the Ackermann function. Let's say a0 of x is x plus 1. So d L of 3 d plus 1 of L d is what? It's d dl. Now I go down the branch one below, and I have to take the first. I have to take L times binary length. It's this one. And then I take the d root of this one. So in total, I get here x. D. I use my estimate from here. This is the biggest L. L is in D. Bandwidth of L. X. So what in this case away, so we have x to the d, 2 to the x, and it's bigger than x plus 1. So it's bigger than L of what? X plus 1 to the x. And x plus 1 is a0 of x. X is big enough. Okay. Now comes argument, and e times 3 plus I have here I plus 1, so I have here I plus 1 plus 1. It is what we now get down. B is PDL. PDL of as a vector one here. D times 3 plus of the same argument. Index L of B. Now comes induction hypothesis for I. So what do I do? I take this term here, plug it in over here. Now I made a mistake. I have to repeat many times because I'm going down in the Ackermann function one index below. So it's an x times iteration. Okay. Now let us carry out one iteration. We get d x minus 1 of n plus 1 of BDL plus 5 plus 1 of 2L x to the d. To this we apply induction hypothesis. We get in the least at big plus E L x minus 1 E times 3 plus 1. We obtain what? 2L I of x okay, now we apply this claim again. So the inner argument is the form 2L something to the d, 2L something to the d. So the next one is Here comes x minus 2, and here comes L. Comes right. That is. Now I do this for all x. So after x many iterations of the induction hypothesis, I get L like a in this term B, which is the same as I plus 1 plus so by magic, you get all branches of the Ackermann function. So in the limiting situation, we get when x is greater than BDL BD plus 4 then the lead is big as L, then it becomes the one so bigger than x. So the Ackermann function of x. That's it. So this function as a function in x is Ackermann x, L and D are fixed. Nice result. And a bit of mysterious, right? Now comes the final result, namely I make the deep root depending on the argument x. And that will be magical. So let H L of x be what? And root of 1 divided by Ackermann function. And then we obtain that B as a start function, we take GL, and then we take HL of say for B plus the constant in B bigger than and this function CB takes some sort of constants for the rounding, and here I have some L this B K something like this. Basically saying what? Do I want to state this in this form? Good question. Yeah. So somehow we see here that this function cannot be primitively recursive because it's able to compose it with some primitive recursive function. We generate a function value which is bigger than the Ackermann. Okay. Now, what do you especially mean with CD? The CD is this. It's a constant which is needed somehow to do all these estimates. So some sort of iterated tau of an exponential function. And this just to survive these estimates. But CD is somehow a small number compared to the other functions.
And the curly brackets is some like
Is it a set or
yeah.
What?
Do you
That's
take a
a max.
maximum or
Right, a good question. But now the proof goes into 2 seconds. So assume that this is wrong. Assume that the Ackermann function of P at least as big as this terminal or in P. Then what? The argument is for I that's equal to B. We have that what? It's Ackermann function inverse. I. So I is less than equal to this number. Ackermann inverse of I is less than equal to Ackermann inverse of this one. Less than Ackermann inverse of this one. So it's bounded by G. So and L of 1 over D bounded by I take this function. And then the function B G L H of L applied to the number. Since the function along which we iterate is bounded by the function HL, we can remove this Ackermann function into the function where we take and here I take the function, let's say, I take a d of L, which is to the 1 over d. I plug in here a d of L. And here I apply my lemma. And this is bigger than L of the Ackermann function. Applied, comes to the argument, but applied to d of the argument. And this is bigger than the Ackermann function applied. And that's the contradiction. Now, what is needed is the monotonicity property of the Ackermann function. This function needs pointwise this function, then this function is this function.
And the definition for the constant C of D is like the sets the maximum of, and then all these numbers E squared blah 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 times this times B of this complex argument, but then the complex argument of the B of GL HL, there is a C of D reappearing, so it's
What? So here,
okay, that's not this condition on, okay.
yeah, it could be just the usual argument. And once you have the result for a fixed root function, then you take the result for a fixed root function, and then you compare the fixed root function with the function where you make the root depending on I. And then you look at compare these two functions, and in the beginning, this function is growing quicker than this function. And then you make your estimate, and then you plug in your bound that you have for fixed D, and then somehow the result comes out. And that's the treatment for the Ackermann function. And this closes basically the whole topic, because at the beginning of the lecture, I want to treat Peres-Serre for dimension 2, Cannon-Moe-Maclaurin for dimension 2, and the Ackermann function. And next time we do something else. So when you found it a bit messy, it doesn't matter. Next time we start with ordinals, and we press phase transitions out of ordinals. And so what I will do is I will first study Y0. Then comes Peres-Serre for unbounded dimension. So with complexities even more complex than the Ackermann function. And we learn how to deal with Peres-Serre. Then I had the result for Cannon-Moe-Maclaurin for unbounded dimension, which I will not cover because it's somehow rather complicated. What then comes is phase transition for Goodstein. And phase transition for what is called the Hydra battle or Hydra game. So it's a topic about certain properties of ordinals. This Hydra game has to do with this Greek mythology. Hercules is fighting the Hydra and he wants to win. And, we prove that he is winning, but also what type of phase transition is involved. So I hope this is interesting. So that's a plan for the next lectures, and this will cover maybe again three lectures, and then we do something else. Then we come to tree, finite trees, phase transition for Brasker's tree theory. Okay, so much for today. And if you have questions, just let me know. There's always a small danger that some estimates are not 100% correct, but I'm quite convinced that if there's something not 100% correct, it is easy to modify it. So there are certain situations where you're not allowed to make small errors. But in these estimates, you see when you do estimates with the Ackermann function, you have lots of space. And some initial values don't fit, you just modify them. Okay, so much for today. And I put recording also on